I wanted to take the opportunity to talk about two geometric series here. Recall from class today that geometric series which we can write out like this, or we can write it as the sum from n equals 1 to infinity of a r to the n minus 1, has the property that it will converge to a over 1 minus r if the absolute value of r is less than 1. But if otherwise, the series will diverge if the absolute value of r is greater than or equal to 1. And so I want to do two simple examples of this here. The first is find the sum of 1/2 plus 1/4 plus 1/8 plus 1/16, etc. When we look at this sum, we first want to consider its type, and it's fairly clear that it is a geometric sum because as I go from term to term, each term is 1/2 of the previous term. So that's what marks it as a geometric sum, with an r value of 1/2 and also an initial value of 1/2. Written in unrolled form like this, it's very easy to pick up the two characteristics. So I can take my sum and I can rewrite it as the sum from n equals 1 to infinity of 1/2 times 1/2 to the n minus 1. If you feel the compulsion to simplify, we could also write this as the sum from n equals 1 to infinity of 1/2 to the n power. But this is really the form that is useful to us. And since the absolute value of r is 1/2, which is less than 1, we see that the series converges. And so our sum is equal to 1/2 over 1 minus 1/2, which interestingly is exactly equal to 1. And the reason that I wanted to do this problem is that it has a very nice geometric interpretation. If you take a square of side 1, and you take that square and you cut it in half, so that this part here has an area of 1/2. And then you take half that remains, so shade all this so that we account for that. Take that half that remains and divide it into 2 equal parts. So this is now 1/4. And then take the part that remains and divide it into 2 equal parts, and what you get is 1/8. And if you continue this process forever, what you will be doing is adding up half and half and half. There's half again, that's 1/16, 1/32, 1/64, and so on. And when you add up the entire thing, then geometrically what we're saying is that the sum of all of these pieces adds up to one whole square. Ta-da. Speaking of geometric interpretations, I want to consider a second problem. A ball is released from a height of 1 meter. Every time it bounces, it returns to 1/3 of its original height. What total distance will it travel as it bounces? So let's draw a picture so we can see what's going on here. My ball is here, and I drop it from a height of 1 meter, and so it bounces like so. And then once it hits, it bounces up to a height of 1/3 meter, which I over drew there. There's 1/3. And of course, once it hits a height of 1/3 of a meter, that's poorly wrong. Let's try that again. This is a distance of 1/3 from here down to the ground. Once it hits a distance of 1/3 of a meter, it's going to fall back down again. And when it bounces, it will now bounce to 1/3 of that height, which is 1/9 of a meter. So it's going to bounce up to here, and then it's going to bounce down again, and then it will bounce up to 1/27 of a meter, and down again, and so on and so forth. It's going to bounce up and down. It will actually keep on, in theory, it will keep on bouncing forever. And if you might be thinking, well, if it bounces forever, then it will travel an infinite distance, but not so. We can actually capture the amount of distance by considering, first of all, the distance down in black, and then the distance up in red. If we consider the down distance in black, then what we have is a distance of 1 meter, plus the next one is going to be 1/3 of a meter, plus the next one will be 1/9 of a meter, plus 1/27, and so on. Meanwhile, the up distance in red is going to start at 1/3 of a meter, and then add on 1/9, 1/27, 1/81st, and so on. And when I write it like this, you can see that the down and the up are separately two geometric series. So that the down is going to be equal to down is going to be equal to the sum from n equals 1 to infinity of 1 times 1/3 to the n minus 1. And the up is going to be equal to the sum from n equals 1 to infinity of 1/3 times 1/3 to the n minus 1. And you can see how easy it is to pick the a and the r out of the unrolled series that we have right here. And having done so, we see that the r is less than 1 for each of these, so that I can immediately write the sum of my series as a over 1 minus r here, and a over 1 minus r here. And when you simplify this guy right here, you get 1 over 2/3 is 3/2. When you simplify this guy, you get 1/3 over 2/3, which is 1/2. And so our total distance traveled is equal to the sum of these two, 3/2 plus 1/2, which is equal to 2 meters. Very interesting that we travel 1 entire meter in just this first leg of the journey, and then all of the rest simply adds up to an additional meter. Well, I hope this was helpful to you in terms of seeing how to sum up geometry.